This next video, we're doing chapter 2.3 and 2.4 together. It's going to be the first and second derivative test and curve sketching. So there's going to be several points that we need to find in order to accurately graph a function. These points are going to be extreme points, inflection points, and x and y intercepts. So there's going to be kind of this general approach that we're going to be doing for sketching curves. We're going to start with f of x. We're going to find the derivative and the second derivative. We're going to find the relative minima and relative maxima, find the inflection points, and study the concavity, and consider other properties such as x and y intercepts, and complete the graph. And from relative minima and relative maxima, we can find when the curve is increasing or decreasing. So let's go ahead and start with locating relative extreme points. So the tangent line at a relative maximum or a relative minimum has a slope of 0. So the way that we find relative extreme points is we take the derivative, set it equal to 0, and solve for x. So take the derivative, set it equal to 0, solve for x, and those will be our relative extreme points. And from that, we get a critical value or a critical number. A number a such that f prime of a equals 0 is called a critical number or a critical value. If a is a critical value, then the point a comma f of a is a critical point. So this just means that when we take the derivative and we set it equal to 0, we solve for x. All of these x values that we get as answers are going to be critical points. They may or may not be relative max or min though, and then we'll see why that is in a second. So in order for a point to be a relative maximum value, the function has to change from increasing to decreasing at that point, and in order for it to be a relative minimum, it has to change from decreasing to increasing. And we know that a function is increasing on the interval where the derivative is positive, and it's decreasing where the derivative is negative. And like we mentioned, not every critical point is an extreme point, as we'll see below in the points in the examples on the right. So first, taking a look at this one right here, we can see that we have a relative or local maximum point at a because it changes from increasing to decreasing. The derivative was positive and then it was negative. So the tangent line here is 0. And then for the next one, we have a local minimum. The derivative is negative, so it's decreasing. Derivative is positive, so it's increasing. Tangent is 0, so relative minimum. And then these ones on the right, this is where we can take the derivative, set it equal to 0, but actually not even get a local max or a local min. So the function would be increasing. The slope is 0, but then it would be increasing again. Or it could be decreasing, slope is 0, and then decreasing again. So if it doesn't change from increasing to decreasing or vice versa, then there's not going to be an extreme point. It'll be a critical point, but it won't be an extreme point, meaning it won't be a relative maximum or a relative minimum. So that's one thing we do have to look out for. So let's go ahead and take a look at the first derivative test. The first derivative test is going to help us find extreme points, relative max, relative min. And this is how we do it. We're going to take the derivative and set it equal to 0, and we're going to find those values. And then we're going to end up making a table, a little number line table. If the derivative changes from positive to negative, it has a relative max. And obviously ignore these, see the figures? I don't have these figures on here. So if the derivative changes positive to negative, that's increasing to decreasing, that's going to be a relative maximum. If it changes from negative to positive, that's decreasing to increasing, that's a relative minimum. And if it does not change signs, meaning it's increasing to increasing or decreasing to decreasing, then there's not going to be a relative max or relative min. So no local extreme points there. Okay, so let's go ahead and take a look at this example. Find the relative minimum and relative maximum points of this function. So we take the derivative, set it equal to 0. So that's going to be the derivative of f of x is going to be power rule. It's going to be 1/3 times 3 is just 1. Subtract 1 from the exponent, and then minus 4x, linear term, constant term, so 3 plus 0. So now we're going to take this and we're going to set it equal to 0, and we get x squared minus 4x plus 3 equals 0. This factors to x minus 3 times x minus 1, and we get x equals 1 and x equals 3. So what we're going to do is we're going to create this table, and we're going to put down 1, we're going to put down 3, and we're going to see what happens with f prime, and we're either going to get positive or negative, and then that's going to determine whether or not f is increasing or decreasing. So what we have to do is we actually have to pick points. We have to pick points on each little interval, so less than 1, between 1 and 3, and then greater than 3. So we always have to choose points in our intervals here. We can pick whatever values we want. It's going to be easier to choose 0 for less than 1, because plugging in 0 is nice. Then we can plug in 2 between 1 and 3, and then we can plug in 4 for greater than 3. Once again, pick whatever numbers satisfy that interval. Pick the easiest ones that you can, though. And what we're going to do here is we are going to plug it in to the derivative. So f prime is x squared minus 4x plus 3. So we're going to evaluate f prime of 0, which is 0 squared minus 4 times 0 plus 3, which is 3, which is positive. We don't care what the actual value is. We just care if it's positive or negative. Since it is positive, I put a little plus by the f prime on the bottom. That means f is increasing. Now if we plug in a 2, f prime of 2, that's 2 squared minus 4 times 2 plus 3. That's going to equal 4 minus 8 is negative 4. Negative 4 plus 3 is negative 1, which is negative. So it's negative, which means f of x is decreasing on that interval. And then the last one is going to be, f prime of 4, which is 4 squared minus 4 times 4 plus 3, which is 16 minus 16 plus 3, which is 3, which is positive, so positive and increasing. So here is what I'm going to do from now on. That's one way that you could do it before I mention relative max and min here. Instead of plugging it into the derivative up here, what you should do, and what I will do from now on, is I'm going to plug it into the factored version of the derivative. It's going to be easier to figure out if it's positive or negative in your head without actually having to calculate it. So let's keep that in mind for the next one. Okay, so we know that we are going to have a relative maximum at x equals 1 because it changes from increasing to decreasing, and we know we're going to have a relative minimum at x equals 3 because it changes from decreasing to increasing. So let's just figure out their y coordinates real quick, f of 1 and f of 3. We're going to plug them into the function, and I'm just going to skip that. I'm sure we can do that. F of 1, we would end up getting 7/3. And f of 3, we would end up getting 1. Okay, so that means we have a, once again, relative max at the coordinate 1, 7/3, and a relative min at the point 3, 1. Increasing to decreasing, relative max, decreasing to increasing, relative min. And then you can see here on the graph that it verifies what we found. Okay, let's do another one. Let's find the relative minimum and relative maximum of f of x, which is 3x minus 1 cubed. So once again, we are taking the derivative and setting it equal to 0. So the derivative f prime of x is going to be, this is going to be the general power rule, right? Because we have a function to an exponent. So bring down the 3 out front, leave the inside alone, subtract 1 from the exponent, multiply by the derivative of the inside. The derivative of 3x minus 1 is 3. So simplify this a little bit. We get 9 times 3x minus 1 squared. And now we're going to take that and set f prime of x equal to 0, just like we did before. So that's going to be 9 times 3x minus 1 squared equals 0. And we can divide both sides by 9. 0 divided by 9 is 0. So we're left with 3x minus 1 squared equals 0. Square root both sides. The square root of 0 is 0. Add 1 to both sides. We get 3x equals 1. Divide both sides by 3. We get x equals 1/3. So making a little table here, we're going to have 1/3. We're going to see what that does when we plug in an f prime, if it's positive or negative, points to the left or to the right, and that'll determine if f is increasing or decreasing. So let's pick points to the left of 1/3 and to the right of 1/3. To the left of 1/3 we can plug in 0, to the right we can plug in 1, which is great because those are going to be the easiest numbers that we can possibly plug in. And if we plug them in, plug in f of 0 and f of 1. So now what you're going to want to do is you want to plug it in. Obviously, we only have a factored version here, so that's kind of nice. If you plug in a 0 into 9 times 3x minus 1 squared, let's just go ahead and plug it right in. That's going to be 9 times 3 times 0 minus 1 squared. So we don't actually care what the value is, we just care if it's negative or positive. So 3 times 0 is 0, minus 1 is negative 1. Negative 1 squared is positive, times 9 is positive. So positive, that means f is increasing. Now we plug in a positive 1. 9 times 3 times 3 times 1 minus 1 squared. 3 times 1 is 3, minus 1 is 2. 2 squared is 4. 4 times 9 is positive, so that's also positive. So f is increasing. And we can see that since it changes from increasing to increasing, it doesn't change. It's increasing to increasing. That means there's no extreme point. So no extreme points. And next we have the second derivative test. So that was the first derivative test, setting the derivative equal to 0, and then coming up with that little number line. For the second derivative test, it's going to help us once again do the same thing, help us find extreme points. This time we're going to be using the second derivative, obviously. So if we know that a function has an extreme point at x equals a, we took the derivative and we set it equal to 0. And if we knew the function was concave up at that point, that means there has to be a relative minimum at that point. That's because if it's concave up, it looks like this. And we know there's an extreme point that would have to be right here, which means it would be a relative minimum. Similarly, if we knew it was concave down at that point, then it has to be a relative maximum. So if it was concave down, it might look something like that. So the relative extreme point would be right there, which would be a relative maximum. So the second derivative test, which I have written down right here, is if f prime of a is 0, so that's our extreme point, and f double prime of a is negative, then there is a relative or local maximum at that point. And then similarly, if f double prime is positive, then there's a relative minimum. So second derivative negative, relative max. Second derivative positive, relative min. And let's go ahead and take a look at these examples. So we have the graph of a quadratic function, 1/4 x squared minus x plus 2 is a parabola, and it has one extreme point. So we want to find it and sketch the graph. So finding the extreme point is going to be finding the derivative, setting it equal to 0. So the derivative power rule is going to be 1/2 x minus 1. And while we're here, we're going to be doing the second derivative test. We might as well take the second derivative. The second derivative is just going to be 1/2. It's good just to do them both at the same time, get them out of the way. And now finding the extreme point, taking the derivative, setting it equal to 0. That's going to be 1/2 x minus 1 equals 0. Add 1 to both sides, multiply both sides by 2. We get x equals, I'll go a little bit slower. We get 1/2 x equals 1. Multiply both sides by 2. We get x equals 2. So now we would use the second derivative test and try to plug that value into f double prime of x, see if it was positive or negative. But f double prime of 2, f double prime of anything is positive because it's just positive 1/2. There's nothing to plug in. So that means there is a relative minimum value at x equals 2. Let's go ahead and just find the y value while we're here. So that's f of 2. Plug in 2 into the function to find the y value, and we would get 1. So there is a relative minimum at 2, 1. And let's go ahead and just graph it. 2, 1 is going to be down here. Not going to be the most accurate graph, so I'm just going to kind of graph it like this, and we're going to say good enough. Ooh, kind of messy. So parabola opening up, and good enough, that is our function f of x. Okay, let's do another example. Let's find all possible relative extreme points on this function and then check the concavity at these points to determine how to sketch f of x. So let's go ahead and find both derivatives right away. Get them out of the way. F prime of x, so power rule, 3x squared minus 6x. And then the second derivative is going to be 6x minus 6. Okay, so finding the extreme points, we take the derivative and we set it equal to 0. That's 3x squared minus 6x equals 0. We can factor out a 3x. We'd be left with x minus 2. And set both of those equal to 0. We get x equals 0 and x equals 2. These are our possible extreme points. Using the second derivative test, we're going to evaluate the second derivative at both of these points. So f double prime of 0 is 6 times 0 minus 6. We don't care what the actual value is. We just care if it's positive or negative. This is pretty obvious. It's equal to negative 6. So this is negative. So negative second derivative means it's concave down, which means that there is a relative max at that point. Concave down means relative max. Plug in 2. 6 times 2 minus 6 gives us positive 6. Obviously positive, that means it's concave up. Concave up means there's a relative min at that point. So now all we need is the y coordinates. So let's just find the y coordinates. I'll label it so it doesn't get too confusing. The y coordinates we need to plug in and evaluate f of 0, and we need to find f of 2. So that's all the way back up to the original function up here, and just plug in 0, plug in 2, and evaluate. You'll see f of 0 equals 5, and f of 2 equals 1. So we go ahead and let's plot those first. F of 0 equals 5. F of 2 equals 1. And we know that there's a relative max at 0, a relative min at 2. So that means it's going to have to change from increasing to decreasing at 0, and then decreasing, and then decreasing to increasing at 2. And that is our function f of x. So relative max at 0, relative min at 2. Okay, so the next thing is going to be locating inflection points. So in this previous example we just graphed this function right here, which a little bit better graph is right here. So the question is, how do we know that it looks like this over here on the left, how we just graphed it, and how we, and where it not looks in it, so it doesn't look like over here on the right with figure 10. So you can see that figure 10, there's a lot more going on here. We have the same 2 points where there's a relative maximum and a relative minimum, but then we have these other points and all of these other things going on. So the question is, how do we know it looked like figure 9 and not figure 10? So the answer here is going to be because of inflection points. Inflection points are going to be located by setting f double prime equal to 0 and solving for x. Once we find the x values where the second derivative is equal to 0, we have to check the concavity at those points using a number line, just like we did with the slope with relative max and min. So let's go ahead and graph this function right here. So let's take the derivative, take the derivative, and then take the second derivative. Always get those out of the way first. So taking the derivative, we end up getting negative x squared plus 6x minus 5. And the second derivative is negative 2x plus 6. Okay, so we got those out of the way. And let's see if we can find any relative max or min. And that's going to be finding the critical points. So finding critical points, that's going to be taking the derivative, setting it equal to 0. That's negative x squared plus 6x minus 5 equals 0. Before we factor this, we should factor out a negative to make the leading term positive. So that's going to be positive x squared minus 6x plus 5 equals 0. Two numbers that multiply to 5 and add to negative 6. That's going to be x minus 5 times x minus 1. And that gives us x equals positive 1 and x equals 5 when we set both of those equal to 0. And while we're here, let's just find their y values so we don't forget. And that's going to be f of 1 and f of 5. So plug both of those in the original function here. I'm just going to skip doing that because I'm assuming that we're all good with that. We plug in 1. F of 1 equals negative 7/3. And then f of 5 is going to equal 25/3. So just plug those in the function to get out the y value. And I'm using f of x. This one says y. Just know I'm using y equals f of x here. Okay, so those are the critical points. And let's use we can use the first derivative test like we did before. But let's use the second derivative test. And this is going to determine if they're relative max or relative min. So we're going to use the second derivative. We're going to plug in our x values. And when we plug in 1, we get negative 2 times 1 plus 6, which is 4, which is positive. So it's positive, so that means it's going to be a relative, that means it's going to be concave up, which means it is a relative min. And let's plug in 5. That's negative 2 times 5 plus 6, which is negative 10 plus 6, which is negative 4, which is negative. Negative second derivative concave down. Concave down means relative max using the second derivative test. And before we plot anything, let's go ahead and take a look at the concavity. Concavity and inflection points. So for inflection points, we take the derivative, the second derivative, and we set it equal to 0. Negative 2x plus 6 equals 0. And solve this for x, we end up getting x equals 3. And technically what we should do here is we should verify that there's an inflection point at 3. So since we're dealing with the second derivative, we put f double prime and then we put f up there. So we pick values to the left of 3 and to the right of 3 and plug them in. If we plug in a 0 and a 4, if we plug in f double prime of 0, f double prime of 0 would give us a positive number, which means f is concave up. And if we plug in 4, that will give us negative 2 times 4 is negative 8 plus 6, which is negative 2. That'll give us a negative number, which means concave down. So since it changes concavity, we know there is a inflection point. And let's evaluate f of 3 to find the y-coordinate. And finding the y-coordinate is plugging it back in the function. And we find that f of 3 is 3. Okay, so let's plot all the points that we have first. We have these points right here. Our extreme points, 1, negative 7/3. That's going to be about right here. And then 5, 25/3. 25/3 is a little bit more than 8, so that's going to be 5, a little bit more than 8. And there's an inflection point at 3, 3. And it looks like that is all we got. So we know that it is we know that this is a relative min and this is a relative max. So we also know concavity. So it has to be concave up over here. So we know it's going to look something like this. So it looks like that. So it's concave up at that point. And then it's going to change to concave down at this inflection point. So now it's concave down. Oops. So something like that. And that is our function. And I'm just going to label it f of x instead of y equals the whole function. I'm just going to label it f of x. Okay, and it's good to just go back and kind of verify that this all works out. Okay, and we'll do a couple more examples here. So we have 3 more examples, and for these next 3 examples, we're going to do all of these perfectly correct. And before we do them, I just want to jump down to this little summary of what we want to do. So we're going to be computing the derivative and the second derivative right away. We're going to be finding the extreme points, and that's going to be setting the derivative equal to 0, solving for x, and we need to determine whether or not they are relative max, relative min, and we can do that using the first derivative test or the second derivative test. And then we're going to figure out what the inflection points are by setting the second derivative equal to 0, and we can come up with a little table if we want to check the concavity. And then there's going to be a couple other things like the y-intercept and the x-intercepts if we can, and put it all together. So let's go ahead and graph this one right here. We have y equals 1/2 x squared minus 4x plus 7. So first step, let's go ahead and find the first and second derivative. That's going to be y prime is, so power rule, that's going to be x minus 4. Y double prime is just 1. So that one's actually pretty easy. We should also recognize this is going to be a parabola that's opening upward, so it's actually pretty easy to graph this one. Okay, so step 2 is going to be finding the, well, I'll leave that as blank and put this as step 1. Step 1 is going to be find the critical points. And finding these critical points, we take the derivative and we set it equal to 0. So that's going to be x minus 4 equal to 0, and we get x equals 4. And this is where we have options now. We can either use the first derivative test or the second derivative test. And once again, I'm just going to call this f of x just because it's a little bit easier to use f of x instead of y, because let's just find the y value real quick and evaluate f of 4. If we plug in 4, we end up getting -1. So there, now we just have the x value and the y value. So we have an option. We can use the second derivative test. We can use the first derivative test. Let's use the second derivative test. And we're going to use the second derivative test to determine if that is a relative max or relative min. So the second derivative test is going to be f double prime of 4. There's nothing to plug it into. It's just a 1, which is positive, which means concave up, which means if it's concave up at the point, there is a relative minimum at that point. And we know that there are no inflection points. There's no inflection points because the second derivative will never equal 0 because the second derivative is just 1. That'll never equal 0. And since we know what kind of function this is, we know it's a quadratic, the only other thing we really have to worry about here is going to be the intercepts. So let's go ahead and take a look at the intercepts. We find the y-intercept when x equals 0. So if we plug in x equals 0 into the function, that's going to give us y equals 1/2 times 0 squared minus 4 times 0 plus 7, which gives us y equals 7. And if we want the x-intercept, that's going to be setting the function equal to 0, 1/2 x squared minus 4x plus 7. We set that equal to 0. We actually need the quadratic formula here. That's going to be x equals negative b, so x equals -4 plus or minus the square root of -4 squared minus 4 times 1/2 times 7 all over 2 times 1/2. So pretty messy. And I'll leave that for you guys to practice, but we should end up getting 4 plus or minus radical 2 for that. And for that, you're going to have to plug this in your calculator to actually get a good value so you can graph it correctly. So, but those are the x-intercepts. We have 2 x-intercepts, 4 minus radical 2 and 4 plus radical 2. And that's enough to graph it. So we have our critical point for -1. That's going to be down here. And then we have our y-intercept at 7, our x-intercepts at 4 minus radical 2 and 4 plus radical 2. That's going to put us about right here and right here. So if we connect them, connect everything, we know it is a parabola. So we know it's just going to be U-shaped, opening up like that. Okay, so that one wasn't too bad because it was just a quadratic. So let's do 2 more examples here. We have a cubic now. We have the so finding the critical points. Finding the critical points, we are going to take that derivative and set that equal to 0. So 1/2 x squared minus 3x plus 5. We set that equal to 0. And if we used the quadratic formula, so try to use the quadratic formula for this, you're going to see that there is no solutions because the radicand, the discriminant is what it's called, what is under the radical is negative. So if there's a square root of a negative, then there's no solutions because we would get imaginary numbers. Okay, so there's actually no critical points for this one, which is fine. And for the next thing, we need to actually go a little bit further with this idea of no critical points. Since there's no critical points, what this actually means is that the function is always increasing or always decreasing. So no critical points, no relative max, no relative min. It has to be always increasing or always increasing. So let's figure that out. We can pick any value we want and plug it into f prime of x. Let's plug in f prime of 0. F prime of 0 is 5, which is positive. Since it is positive, that means it is increasing. F of x is increasing. And just like we said, it's going to always be either increasing or decreasing. So f of x in this case is always increasing. So this is a strictly increasing function. And the next thing, let's go ahead and figure out the inflection points. Inflection points means we take the second derivative and we set that equal to 0. So that's going to be x minus 3 equals 0. Nice and easy, we get x equals 3. So we have to be sure that that is an inflection point. That's when we have to use the table. So we have 3, we have f double prime, we have f. Plug in values to the right of 3, to the left of 3. We should use 0 and 4. Those are going to, looks like those are the easiest ones. If we plug in we have to plug into f double prime. F double prime is x minus 3. If we plug in a 0, 0 minus 3 is negative. That means concave down. If we plug in a 4, 4 minus 3 is positive, so concave up. So since it changes concavity, there is an inflection point at x equals 3. And let's go ahead and figure out the y-coordinate. We figure out the y-coordinate by plugging it in that nasty looking function. And we get f of 3. We plug that in. And we get 7. Okay, and it actually looks like that's almost done. Let's find some intercepts here. What we are going to do for this one is we're going to find the y-intercept. Finding the y-intercept is easy, right? Because that's just plugging in 0 into x. So plugging 0 into x, it's very easy just to look at it when it's a polynomial and figure out your answer. That's going to be 0 plus 0 plus 0 plus 1. So that gives us f of 0 equals 1. And what we're going to do for this is we are going to omit the x-intercepts, because if we did the x-intercepts, we would have to set the cubic equal to 0, and that would be very, very, very messy. So we're just going to omit it for this one and just trust that we have enough information. So let's graph what we know. We have the y-intercept at 0, 1. We have the inflection point at 3, 7. And we know that this function is always increasing, and it looks like that is all we have. So that's actually enough. So it's going to look something like this. And it doesn't have to be perfect. It just has to be good enough, and that is good enough. That is our function f of x. So notice that we do have this inflection point right here because it changes from concave down to concave up at that point. Notice that the function is always increasing, so it is accurate enough. Let's do one more. I believe that's one more. Yeah, one more example. We have the function x minus 2 to the 4th minus 1. So I'll start by taking the first and second derivative. The first derivative is the general power rule. Bring down the exponent, keep the inside alone, subtract 1 from the exponent. The derivative of the inside is just 1, and then the derivative of minus 1 is 0. Second derivative, we have 12 times x minus 2 squared times the derivative of the inside, which is 1 once again. So let's go ahead and find some critical points. So finding the critical points, we take the derivative and we set it equal to 0. And that's going to be 4 times x minus 2 cubed equals 0. Divide both sides by 4. We get x minus 2 cubed equals 0. Take the cube root of both sides. The cube root of both sides is, the cube root of 0 is just 0. Add 2 to both sides, we get x equals 2. So here is an issue. If we try to do the second derivative test, we cannot do the second derivative test because f double prime of 2 actually equals 0. So that wouldn't actually help us here. So we're going to have to do the first derivative test. So applying the first derivative test, we're going to have to come up with a table. And that's going to be using the value of 2 and seeing what happens to f prime and how that affects f. So pick value to the left of 2, to the right of 2. It's going to be easiest to plug in a 0 and then plug in a 3. So plug in a 0 into f prime. 0 minus 2 is negative 2. Negative 2 cubed is negative 8. Negative 8 times 4 is negative. So that's going to be negative, so that means f of x is decreasing. Now we plug in a 3. 3 minus 2 is positive. 1. 1 cubed is positive. 1 times 4 is positive. So f is increasing. So that tells us there is a relative min at the value x equals 2 because it changes from decreasing to increasing. That means it's a relative min. And let's find the y value by plugging in 2 into the function. If we plug in a 2, we get 2 minus 2 is 0. 0 to the fourth is 0. And then minus 1, so negative 1. And we know we have a relative min there now. And something we don't have to worry about is finding the inflection point. Since we just said that f double prime of 2 equals 0, then we might think that that is the inflection point, but it's the relative min, so it cannot be the inflection point. So we actually don't even have to worry about it here, so we can skip it. And for this next one, let's just find the intercepts. So let's go ahead and find the x and y intercepts. Finding the y-intercept is evaluating f of 0. So f of 0 is going to be 0 minus 2 to the fourth minus 1. That's going to be 16 minus 1, so 15. That's the y-intercept, which isn't on our graph. And finding the x-intercept, that's going to be setting the function equal to 0, which is x minus 2 to the fourth minus 1 equals 0. We add 1 to both sides and get x minus 2 to the fourth equals 1. Now we take the fourth root of both sides. Since it's an even exponent, we're always going to get plus or minus, just like the square root. So it's plus or minus the fourth root of 1. The fourth root of 1 is just 1. Now we add 2 to both sides. 2 plus 1 is 3. 2 minus 1 is 1. So we get 1 and 3. Let's put everything together here. I'm going to say that our y coordinate up here is 15. And we have 1 and 3. And we know that our relative min was at 2, negative 1. And I think that is all we had, and that is all we need. And we can go ahead and graph it. And that will be f of x. So that was a degree 4 polynomial. Sometimes, like in this case here, it looks similar to a parabola. It won't always look like a parabola, but in this case it kind of does. but a lot more intense in terms of the steepness of the slope. Okay, so that is it for this chapter.